Performance tuning is very important when we develop a solution and we are seeing performance issues. We want our solution to be responsive so that our users will use it. Let's talk about how we do performance tuning when we do data work. Here are the common areas we need to look into when we do data work and we are seeing performance issues. Database server memory, indexing, and code. We'll talk about each of these areas in more details next. First, we will see how we can investigate the database server memory utilization. If we see performance issues, we are using SQL Server for our discussion here. We will run several queries to find out the state of the database server memory utilization. We will be using the dynamic management views in our queries. In this query, we will find out how much is the total memory. Also, what is the available memory on the database server. The database server tends to use all of the database server memory. Therefore, if the available OS memory is low, that's very common, not a problem. In this memory, we will find out whether we have any memory constraint. This query returns the physical memory of the database server and also whether we are having any constraint with the physical memory or the virtual memory. Virtual memory includes paging to the hard drive. We got 0 for both indicators, so we are fine here. If any of these two indicators is 1, that means we have a memory constraint. In this query, we will look at the total server memory as well as the target server memory. The target server memory is the ideal amount of memory the database server can consume or will need to consume, considering the regular workload. If the target server memory is much higher than the total server memory, then we may have memory constraints. We should consider a memory upgrade. In this query, we will look at the page life expectancy. The threshold is 300, that's 5 minutes. Simply speaking, we want to see whether queries can get the frequently used data from the database server memory instead of having the database engine going to the hard drive to get the data. If a query can get the data from the database server memory, then the response will be much shorter. In other words, the performance will be great. If the database engine needs to go to the hard drive to get the requested data, it's going to take much longer. Therefore, performance may degrade. If we have gone through the above steps and we have not seen any issue, but we are still suspecting there may be a memory constraint. Then we will need to do in-depth memory diagnosis by using more advanced code or more advanced tools. Next, we will look at if we have a slow-running query, whether an index can help. We have a slow-running query here. This query takes more than 3.5 minutes to complete, and we will see whether we can improve its performance. To do performance tuning for a slow-running query, we need to use some tools. First, before we run any performance tuning or before we run any test, we want to clear the database server memory buffer and the cache so that we can get the accurate statistics. We can just run this group of codes. This group of SQL statements will clear both the database server, memory cache, and the buffers. We need another tool. We will get the execution plan. Whenever we run a SQL query, the database engine will need to parse the code, and it will need to come up with an execution plan. In the execution plan, there are detailed steps the database engine will need to go through to get the data we are requesting. And I'm using SQL Server Management Studio, and we can get the execution plan from the top menu, select query. There are two options. One is the estimated plan. The other is the actual plan. For this slow-running query, we will look at several scenarios to see whether an index can help or whether an index can improve the query performance. There are 4 scenarios. In the first scenario, we will not create any additional index. In scenarios 2, 3, and 4, we will be creating different indexes, and we will see whether an index can improve the query performance. And this is the first scenario. In the first scenario, we don't have any additional index. We are just using the existing indexes available in the database. And I'm using AdventureWorks 2017 for our discussion. For this query, it will take more than 3.5 minutes to complete to get the data we want. And if we get the execution plan, the plan is displayed down here. You can see the detailed steps the database engine will need to go through to get the data we are requesting. And most of the time will be spent on sorting. It's here. 93% of the execution time. This gives us some hints on how we can possibly improve the performance of this slow-running query. Go back to the code. You can see we do sorting here, order by, total due, but we are getting the highest order values for a customer because we are also using rank and we partition by customer ID. Therefore, when we think about sorting, we need to think about the big picture. Rank, partition, and order by, not just order by. In the second scenario, we will create an additional index, and the columns that we are using for this index are customer ID and total due. The reason why we are selecting these two columns is we are getting the highest order values, that's the total due value for each and every customer. Create this index, and we will run the query again, and we can see the execution time went down to 1 minute and 45 seconds. It's roughly a 2-minute improvement. In scenario 3, we will create an index on just one column, total due of sales order header. And we ran the query again. The response time was 3 minutes and 46 seconds. No improvement, simply speaking. This index didn't really help because what we want to get is the total value of a customer, not just the total value in general. But we are creating the index only on this total due column, therefore this index cannot help. In scenario 4, we will create an index. The index will be based on 3 columns, customer ID, order ID, and the total due. This index worked a little bit better than the index we created in scenario 2, but not much. The response time went down to 1 minute and 39 seconds. Go back to scenario 2. Response time was 1:45, and the index was based on 2 columns, customer ID and the total due. In conclusion, we can create an index based on these 3 columns, customer ID, sales order ID, and total due, to improve the query performance, and the response time will go down from 3:33 to 1:39. A 2-minute improvement. Quite good. Just keep in mind, when we try to get the performance statistics, when we run performance tests, we want to clear the database server, cache, and the buffer so we can get the accurate statistics. The third area is about the code efficiency, and we will look at two use cases. In the first use case, we are looking at this query. This query doesn't look very sophisticated, but the performance was horrible. It ran for 11 hours without returning any data. The code is not complicated. The challenge is that there was so much data. We had several tables. In each table, there were billions of records. That's billion as B, okay? Billion. A lot of data. To improve the code efficiency, I broke up the query into two smaller queries. The first query ran for about 10 minutes. The second query took about 2 minutes. In other words, in 12 minutes, I got the data I wanted. So it's a huge improvement because originally it took more than 11 hours without returning any data. You could have run for another several hours easily. But after the improvement, after the code re-engineering, it took only 12 minutes to get the data we wanted. This is the second case for code efficiency, and we will revisit the slow-running query we looked at earlier. Remember, this query took 3 minutes and 33 seconds to complete. We will see whether we can re-engineer the code a little bit to improve the query performance. Take a very close look at this code. We are getting all the values for each and every customer, and we are doing the horizontal reporting format. In the subquery, we are getting the orders. But you look at this code, we have the subquery, we have the outer query. In both queries, we are doing the work at the sales order header level. But what we are wanting to do is to get orders for customers, right? Therefore, in the subquery, we need to do the work at the sales order header, the hierarchical level. But in the outer query, we should do the work at the customer level. It's a higher level of the data hierarchy. That's a candidate for performance tuning improvement. Maybe we can try that. So if we update the code and in the order query, we do the work at the customer level, look at the updated code in the order query. We are using the customer table instead of doing the work at the sales order header level again. Then the response time went down from 333 to 302. That's a 31-second improvement. it helps. If we create an index, an additional index on these 3 columns, customer ID, sales order ID, and the total due ID, not ID, total due value of the sales order header table, then the response time will go down to 1 minute and 23 seconds. This is a huge improvement. The original response time was here, 3 minutes and 33 seconds. By doing 2 things. Number 1, we did a little bit code reengineering. Number 2, we created an additional index. Then we improved the query response time from 3:33 to 1:23. A huge improvement. An improvement of 2 minutes and 10 seconds. We have gone through some details and steps about how we do performance tuning when we do data work and if we are seeing performance issues. This is a very good starting point for how we can do performance tuning to improve our solution improvement, especially if we have slow-running queries. This is the end of our discussion.